Oh, yeah, I bet.
About $3,000 ahead.
Oh, yeah.
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 For a couple days till you buy
Okay.
something.
Yeah. Well, maybe that's down the road for me. We'll see. Okay, well, welcome to class, everybody, and hope you're having a good day. And I didn't realize how green this shirt was till I saw it on the monitor back there, man. So this hopefully will keep us all awake. So it's bright green. I curved the first exam 6 points, so hopefully everybody got the 6 points. Make sure you did, because they kind of had a hiccup or two with folks on that. The way I had to do it is you go in, you answer a silly question, and then it gives you 6 points. So if you'll do that, we'll be good. I generally do that. I'll take the high score in a large course like this. Well, I think we had about 65 people take the exam, so I'll take the high score, which was 93 point something, I forget, and make it 100. So that's why I added 6. So hopefully that's fair. But let me know if you, also tomorrow I'll try to update your scores on Blackboard as far as your averages go. I'll try to do that on Friday. So I know not all of your scores are coming in from Connect to Blackboard. You know, it's just, I don't know, there's not complete compatibility there. So I have to manually do that. So as far as the total goes. But at semester's end, I download your grades from Connect. So don't worry about losing any of your scores. You'll get, if you did an exercise that's not reflected on Blackboard, you will still get credit. Okay. All right, so today, I want to wrap up our conversation about Chapter 7. We had gotten into Chapter 7 last time, and we may have a chance to look a little bit at Chapter 9. We'll skip Chapter 8 for now anyway. But we were looking at utility maximization last time, and we saw this graph. It's in your book on page 137. I think I'll just stick it under the doc cam here, just to make sure we know what we're talking about here. Illustrates diminishing marginal utility. Now, we're going to have, this is like the second law, okay? We're going to have like 3 laws. They're not Newton's 3 laws, they're microecon 3 laws, I guess. So we've talked about a law of increasing marginal cost. We'll come back and look at that again, but we were looking at that in the context of constructing a production possibilities curve and so forth, frontier. And also we're going to see that in production. And when we get to Chapter 9, we'll look at short-run production relationships, and we're going to bump into that law again. So you had the law of increasing opportunity or marginal cost, okay? So, I mean, you hear that a lot. This second law is the one we revisited last time. It's embedded in this diagram or this discussion here. Law of diminishing marginal utility. And then later today, perhaps if we get to Chapter 9, we'll talk about another law, okay, a law of diminishing marginal product, and that deals with production. But here we're talking about consumers. We're talking about consumer behavior in Chapter 7. And of course, what consumers are looking for is utility, okay, satisfaction. There's that song, Can't Get No Satisfaction. Remember that? So this is, you got a certain amount of money and you can consume goods. You're looking for satisfaction. So the idea is to increase the level of satisfaction from your consumption. So we looked last time at a two-good situation where we make use of this law here to determine the right mix of those two goods to consume to optimize your satisfaction or utility. But here we're just looking at one good, consuming successive units of one good. And you have this total utility curve here. Say, picture here in your text. And the thing to remember, we're going to make use of this more in Chapter 9 as well, but the marginal utility is the additional utility derived from the next unit, say, okay, or on just one unit. So this particular good experiences increasing total utility for the first, looks like 5.5 units. So the 5th unit and the 6th unit a total of 5 units or a total of 6 units is going to deliver the same amount of satisfaction, if you will, because you max out the total utility right here at 5.5 units, okay? So if you don't care how much you spend on this one good, you just want to maximize total utility, then if that's your goal, then you purchase and consume 5.5 units. Of course, if you got another good competing with this, then you're going to look at the prices of each too, right? So if another good delivers more total utility, maybe its curve goes up here, but heck, it's a lot more expensive, then you're not simply going to jump on that good, because ultimately what you care about is this, what I call bang per buck rule last time. You want to maximize across all of your consumption, you want to maximize marginal utility per price for each good in your consumption bundle. But here we're just looking at one good, and what is typically true here is that as you consume more units, additional units of that good, then the additional satisfaction delivered by the marginal unit is going to decrease. So this thing's still going up, but the additional satisfaction is diminishing. It begins right away, okay? And then it turns negative. Now we see here in what's called the marginal utility curve, below it here, we see that this curve gives you the rate of change of the total utility curve. This is the marginal utility curve. And a thing to note here, and you can see it over in the chart on the left if we look at that just a second, but you see it graphically as well, is that at the level of consumption, you always have to have a time frame here. This is per meal. Could be so many pizzas per week or per year or what have you. But within a time frame here of one meal, total satisfaction is maximized at 5.5 units, maybe slices of pizza or what have you. At that value of consumption, you look down here and we have the same x-axis, if you will. This is quantity consumed. At that level, marginal utility is 0. Okay, so this is the marginal utility curve. Marginal utility will be 0 when total utility is maximal. Okay, we're going to use this again when we talk about production theory in a little bit. We'll talk about total product and marginal product and so forth. Just a relationship here. The marginal gives you the rate of change of the total curve. And so this total curve is always, if you will, it's diminishing in its increase in this thing right here in total utility. The total utility per unit for successive units is getting smaller. So this is bigger than this, is bigger than this, is bigger than this. So we track those, if you will, those rectangles. This one here is 10, so kind of over the average of the first unit here. Marginal utility is 10 units. And then here it looks like that. I don't know, you go from 10 to 20, it looks like about 8. Well, son of a gun, it is for the second unit. Okay, here's 0. You have marginal utility of 8. So I hope you see that. We're basically taking these rectangles and stacking them down here, okay? Of course, this one becomes negative. So marginal utility tells you the rate of change of total utility. Now, again, what we were doing last time, though, is we make use of that. We compare marginal utility. We recognize that as you consume more and more units of the good, marginal utility goes down. And I asked you to think about this question last time, and we actually used a relationship from this to solve the optimum consumption problem for two goods. But if the marginal utility of A is less than the here we go, over the price of A is less than the marginal utility of B over the price of B. That's not a B, that's a B, okay? So last time we used the fact, we put an equal in here, okay? Put an equal sign. We said that was the utility maximizing rule. That is to say, we did a little chart, if you'll recall. We had two goods, apples and oranges, and we said if you have $12 budget or $24 budget, how are you going to allocate your spending between the two goods? So we spent successive dollars. Okay, we peel those dollars off, and we would always seek the good with each marginal dollar, if you will. We'd always seek the good that has the highest bang per buck. Remember that? so that eventually you get an equal, close to an equality here once you've spent all your money. Okay, so what happens is marginal utility of both goods decreases as you consume more and more of those goods. So this may be true for a little bit, but if you look at this, you'd say, oh, I need to consume B because this fraction's bigger than that. That's how we made our decision at each step. And so when you do that, you consume more of B. Guess what? Because of diminishing marginal utility, this thing's going to go down. And so this fraction is going to shrink. And what happens if you continue to, with each successive dollar, purchase the good A or B that has the highest marginal utility per unit, eventually you're going to get very close to marginal utility of A over price of A is marginal utility of B over price of B. So I'll put a box around that one. We call that the utility maximizing rule. Bang per buck rule if you want, or also a lot of times you'll hear it called the rational spending rule. I always like that, rational spending rule. Rational spending rule, because a rational person, one who's always, no, not just willy-nilly, say, I'm going to buy some apples, and maybe you hate apples, or what, you'd rather have oranges, I just buy apples. Okay, a rational person's always going to act in their self-interest, economically speaking. So as you spend your budget down, you're going to approach this condition here, and if you don't satisfy this, then you haven't really allocated your budget to the goods, in purchasing the goods that delivers the most satisfaction. You bought too many apples, not enough oranges, what have you. Too many oranges, not enough apples, once you've spent all your money. Now, so you always seek this thing, even if you have 100 goods or 1,000 goods. And typically, as Americans, we have many, many goods to choose from. Believe it or not, intuitively, I mentioned this last time, the brain is an amazing computer. I mean, God made the brain like it's super sophisticated. They talk about artificial intelligence, but I just don't think we're ever going to get there. I guess artificial intelligence is something great, but all the mathematical calculations you do as a human being, if you had to program a computer to do those things, it would take lots of code. It'll take lots of code. I think I mentioned the passing problem in traffic last time. Same sort of thing. So if you have 1,000 goods, you're always seeking to get an equality here. So until you get to this point, you'll have something like this, okay, right? And so always you purchase the good that delivers the most bang per buck. So the idea here is since this is greater than this, then you purchase B first. Okay, so you're going to purchase a unit of B. I actually, last time asked, with respect to this relationship, to think about this a little bit. For fixed prices, we're assuming a consumer has no power over prices, kind of a competitive situation. And this is the case for most situations. When you go to Walmart, you buy a head of lettuce, you're not going to bargain with a cashier, right? Cashier's not going to say, we're getting a little low on lettuce, I think we'll charge you a little more. It doesn't work that way. Now, there's some things you can bargain over, a car and a big item, but generally speaking, as consumers, we don't have any power over this, okay? But we do have power over the marginal utility that the last unit of A we consume will compare with the last unit of B. So we have power over this. These are driven by our consumption levels of A and B by the law of diminishing marginal utility. So that is to say, okay, if this is the situation temporarily, we still have income to spend, we're going to purchase B. But guess what happens when we purchase B? Marginal utility of B goes down, right? It's going to go down. Or I kind of couched the problem this way last time. I said, what if this is true at the end of last week? You get paid every week. You spent your last dollar. And the last unit of B that was purchased delivered more marginal utility per price than the last unit of A you purchased. So however many apples, we'll call these apples and these oranges. Should have used an O there, I suppose. But if that were the case, last week you spent all your paycheck, you bought A and B, apples and oranges. You look at this, if this were true at the end of that week, and then you get another paycheck this week, you say, hey, can I do any better in spending my paycheck this week? Yeah, you can. By purchasing more B If you purchase more B on a fixed income, that means you're going to purchase what? Less A. So the idea here is you purchase more B. Okay, so I'll put the word more in here if you will. So if this is true at the end of a time period and you get to repeat the experiment the next time period, you got the same paycheck and so forth, prices don't change, you should purchase more B, purchase what? Purchase less A, if you can read my writing here. Now what happens if you purchase less A? Marginal utility of A goes up. Now, got to be careful. This may move in the way opposite than you might intuitively think. But remember, it's diminishing marginal utility. So if you purchase this week less units of A than you did the previous week, then that last unit of A you purchased is going to deliver more marginal utility. Okay? Because marginal utility decreases with consumption. So if you consume too much A, then the marginal utility of A is too small. Really what we want to do is reallocate that paycheck we get each week, fixed paycheck, so that this goes up and this goes down. If we'll do that, then we will arrive, if we do it right, we'll arrive at the rational spending rule or the utility maximizing rule. So consume more B, I guess we consume more B and less A. Now, so this is where I asked you to think about the diamond water paradox. There's a discussion about this in your book, The Diamond Water Paradox. So this is, they call it a paradox. It's true, but I guess you'd say it doesn't seem that it should be true. You know what a paradox is, really? Paradox is something that can be neither true or false, okay? Like if I wrote, I'm taking an aside here just a little bit, but if I said this sentence is what? What do you think? This sentence is false. If I said that, it's a little aside, but I got to do something with it. This sentence is false. Well, that's called a paradox. Why? Because if you assign a truth value to this, it's futile. That statement can be neither true nor false, okay? Because if it's true, it's false, and if false, it's true. I don't know if that makes sense or not. There's another one you might look up called the barber paradox. It's a very famous paradox. A barber in a town shaves exactly those who don't shave themselves, who shaves the barber. So you can Google that, the barber paradox, if you're interested. It has no solution. You can't say it's true. You can't say it's false. Okay, so the diamond water paradox, in a way, they call it a paradox, but it's just something that's intriguing. And why is this? Because here's the deal. We all know that water is more essential to life than diamonds. Everybody knows that. Everybody knows water's more. You got to have water to live, but you don't have to have diamonds. Unless you're Elizabeth Taylor, you don't have to have diamonds to live. But why is it then that the price of diamonds is so much higher than the price of water? Okay, so if you want to buy a pound of diamonds, I don't know how many carats that is, and I know it all depends on clarity and all that, but just say a unit, just a small unit of diamonds, whatever the weight is, it's going to cost you a whole lot more than the same weight of water. Why is that? When water is more essential to life than diamonds, why is, if you went out to the marketplace and said, hey, I want to buy a bottle of water or I want to buy a bottle of diamonds, you're going to pay a lot more for the diamonds. So water is more essential to life, but why do diamonds cost so much more than water? What do you think? I mean, it's... Okay, yeah, supply, exactly, in that the water, I mean, water's everywhere, right? Water. So Coleridge said, water everywhere, but not an ounce to drink, something like that. But he was out in a boat looking at the ocean. But we got water all around us, right? So there's a great supply. Exactly. Because water is ubiquitous. Now, many places of the planet, it's not, of course. Certainly, if you were in the Sahara Desert and you're thirsty and you've walked 100 miles and you come upon a trader with a train of camels and they say, what you want to buy? A bottle of water or a bottle of diamonds? You'll probably buy the water in that situation. Of course, in that situation, For you, water is scarce. But it has to do with scarcity and supply. The thing is, of course, then the question is, why is the price of diamonds, we'll just say P sub D, so much greater than the price of water? And as you mentioned, it has to do with supply. Here's the deal, of course, because there's so much water, and we can consume water kind of at will, there's no big deal there. Since this is true, since what we have observed is the supply of diamonds is much less than the supply of water. Since the supply of diamonds is so much less than the supply, or S, of water, just abbreviate there. Since that's true, then in our normal consumption pattern through a day or what have you, as we drink water through the course of a day, as we buy diamonds through the course of a day or year, the last unit of water we consume has a marginal utility that's much less than the marginal utility of diamonds. So this would be true. This would have to be true for the last unit we consume in a time period. So be it a day, be it a month, be it a year. I'll just say for the last unit typically consumed, okay? For the last unit typically consumed in a week or what have you, it got to be the case that the marginal utility of diamonds is much greater than the marginal utility of water. And if that's because there's so many more diamonds, we don't get to consume that much in the way of diamonds, but we have a lot of water. You can keep drinking water until you're tired of water, okay? And most of us can. 95% of the population around the world has probably pretty much free access to water. There's people, I know people who do mission work and so forth in Africa, and they dig wells. So maybe it's not 95%, but these poor people, some of these villages, all they want is water. You know, if they could get water, they could live like they would want. But for most of us, certainly in the United States, that last unit of water doesn't deliver as much additional satisfaction as that last unit of diamonds. Well, because of that, okay, if you compare the marginal utility of diamonds to the marginal utility of water, to their prices, the price of diamonds and the price of water, then since this is so much bigger than this, the only way we ever achieve this equality here, this utility maximizing rule, is this must be much larger than this, okay? In other words, the marginal utility of the last unit of diamonds is so much greater than the last unit of water, means that the price of diamonds has to be much greater than this for the two fractions to be the same. We all kind of know that relationship with fractions. So if you got a bigger numerator here, you need a bigger denominator here. So since this is true for the numerators, this is bigger than that, then we can say here that the price of diamonds has to be greater than the price of water. In fact, I'll put a 2 thing here. It's much greater, okay? Whoops, sorry about that. So since this is true, making this numerator bigger than this, for this to be satisfied, which we're all seeking to do, then the market will adjust these two prices so that you have equality for the typical consumer. So the price of diamonds must be much greater than the price of water. So again, it's not the price of diamonds. You might think here, just a second, we think supply and demand. And we think about prices being determined by total supply. But in this case, it's not, the prices are driven by not total supply or total utility derived from all that we consume. Total utility has nothing to do with getting to this relationship here. Total utility has nothing to do with it. In fact, you get a lot, if you think about it, if you go out and buy diamonds, you will pay a lot more for it because you value that last unit of diamonds more than the water. You'd give up a little water to buy some diamonds. But you wouldn't give up all the water you drink for any amount of diamonds because you got to have water to live. So this has nothing to do with total utility derived from consuming diamonds of water. It has this relationship as a result only because we derive more satisfaction from the last unit of diamonds consumed compared to the last unit of water consumed. Okay, so prices will adjust in that way. So it's these marginal values that drive the prices to where they are. Okay, so this relationship here, though, the equality of marginal unit to price over all the goods you consume, be it water, diamonds, apples, and oranges, and whatever it is, that is a condition we all seek to satisfy. Everyone seeks this thing right here. If temporarily this thing is not in equilibrium, then you will, if you're a rational person, you'll do what we said here. You'll consume or purchase more B to drive this down. You'll purchase less A to drive this up. I want you to make sure you kind of have this in your gut, so to speak, okay? Is that the dynamic here is we're always seeking to achieve equality. And the way we get there is by taking recognition of the law of diminishing marginal utility. So when you have a situation like this and these two fractions are out of balance, you need to drive this one up. And then your thinking should be the following. It shouldn't be just say, oh, I've got to get equality here. The linkage here is you drive this fraction up by driving the numerator up. You drive the numerator up by consuming less A. Down here, you drive this numerator down to drive the fraction down by consuming more B. And that's the law of diminishing marginal utility. So I spent enough there. I just want you to think on this as one of those relationships I hope that we can kind of become intuitive about, okay? We can like I say, feel it at the gut level. Okay, any questions on that? Okay, all right, so what I want to do then is I want to look at a little bit of the theoretical underpinnings of the law of demand here to close out Chapter 7. There's a discussion in the appendix to Chapter 7. We're going to look at that here next. So if you have your text, and I'm fond of saying you'll have to take out your appendix, and we'll look at this in Chapter 7. So, okay, all right. Okay, so I'll tell you what. Oh, yeah, let's do that. Let me... Oh, I couldn't have said that better myself. Okay, somebody must have an AI professor out there. Okay. Let's see here. Dr. J's a little... I'm glad that happened because it gives me a chance to figure out. Last time you might recall that we looked at... the law of demand for normal, applying it to normal and inferior goods. In general, there's two effects that contribute to the law of demand. What's the law of demand? In a period of time, as the price of a unit goes up, because a good goes up, the quantity demanded goes down. Yeah, that makes sense. There's two reasons. I mentioned two reasons why that happens. There's the substitution effect. So just think in terms of two goods, A and B for a minute. If the price of A goes up, then A becomes relatively more expensive than B. And that's a ceteris paribus. Nothing else changes. We're not messing with the price of B. But if the price of apples goes up, then we substitute away from apples to oranges because it's relatively more expensive. But then there's also the income effect. That's a whole different cause and effect here. Another reason why for apples, which is a normal good, we would consume less apples is because when the price of apples goes up, your real income does what? It goes down. The things that you typically put in your shopping cart, you always buy apples and oranges. The price of apples goes up, you can't put as much. Now your real income's the real stuff you can buy on your nominal income. So that's called the income effect. And for most goods, we call normal goods, if you experience a decrease in income, you demand fewer of those goods. Those are called income normal goods. Okay? Now there are a few goods like ramen noodles, I keep using that, black and white TVs, compact cars, efficiency apartments. Some of these things that if your income goes down, you might buy more of those. So you might be in the market for a subcompact car if your income, if you got to cut and pay, right? So forth. So we made this little chart last time. Remember, we talked about the substitution effect and income effect. I thought I had this with me here, but you remember I drew the arrows. Go back and look at that, okay? But we saw that, and let me just kind of summarize this for a second. We saw the following here. For income normal goods, we saw that the substitution effect and the income effect move together. Okay? So, that is to say, both of these things will drag down your consumption of a normal good when the price of the normal good goes up. Because the good becomes relatively more expensive and your real income goes down. But for inferior goods, okay, for inferior goods, the substitution effect moves oppositely from the income effect. Now, the substitution effect's pretty obvious, I think, but what we're saying is that if there's a price increase, then you're always in the substitution effect, you're going to consume less of the good. Okay, that's pretty obvious. But here, inferior goods, if there's a price increase in apples, your real income went down, and so you consume fewer. Okay? Did I get that right? In an income inferior good, if your income goes down, you consume more. Okay? So, again, the price of apples, I got to put something there, goes up. Then we had these two effects. We had substitution effect, and we had income effect, and then we had net over here, okay? And I drew this arrow here. It looked like that. This is one line in that table I had last time. If you don't remember that, go back and look at that. But the income effect is opposite of the substitution effect. And I drew a little arrow here. But the first point is they move in opposite directions. So if the price of apples goes up, you're going to substitute away from apples to oranges, but also because your real income went down, and apples is not a good one, ramen noodles, say, that's an income inferior good. You're going to consume more. On net, though, this is always bigger than this, so you're going to get this thing here. The thing to note here is that always the case is that the substitution effect will swamp. I'm going to use the word swamp. Swamps the income effect. That's why I drew a small arrow here. I hope that makes sense. What I'm trying to say here is that income effect is significant, but it's not as big a deal as substitution effect. Now, we're going to see graphically here in a minute kind of why that's true, okay? That's why if you go to the appendix here, and we're going to see why the substitution effect always swamps the income effect. But let's just talk here about it. I'm going to come back to this here a little bit. You should be able to fill out that chart I had last time. Remember, there were 3 other rows. Okay, go back and look at that. But if you had price of an inferior good go down, this arrow goes up, this one goes down. Okay, go back and look at that. And then you got abnormal goods. There were 3 other lines in that chart we did, but I'm not going to do that today. But we're going to look at the appendix here. And what we have to see here is that in indifference curve analysis, there's some things they note. First off, utility is difficult to measure, as we mentioned before, because we may talk about a unit of utility, a util, say, but I mean, to you, an apple may deliver 5 utils, whatever util is. To me, it might deliver 10, okay? So it's very subjective. What is a util? I don't know, it's not like a pound or a kilogram or something like that, or a foot or meter or anything like that. It's kind of difficult to measure utility. However, we can talk about one good having more utility than the other. Okay, so when we talk about comparing consumption bundles, we can compare their utilities in that we can order them, I guess you'd say. I'd rather have an apple than an orange. But it's kind of hard to say. I'd rather have an apple twice as much as I would an orange, or 1.5 times as much as an orange. That's kind of hard to do. So ordinal, you can kind of order consumption bundles, but we try at any rate in math to apply units to look at how you get to this optimal consumption pattern. So when we talk about marginal utility and so forth, it's an effort to quantify utility, but it's kind of hard to measure utility. I don't have a utilometer hooked to my body, so when I eat a donut, okay, the needle moves, but that's what that would be. But we can rank or order preferences for products, okay, when we talk about utility. But we're going to take into account the consumer's budget when we do so, and we looked at last time how you drive the demand curve. We actually did that on a fixed budget last time. So I want to just review this a second. When I said a fixed budget, there's this budget line concept. It's a combination of two goods that a consumer can purchase with their money income. So we're going to assume a fixed income here, and you purchase A and B, whatever it is. It turns out that the slope of the budget line is the ratio of the price of B to the price of A. I'm going to come back to this in a second. I've given you guys these slides here on Blackboard, but I thought we'd just look at this one just a second. Hope I got it all on there. Consumer's budget line. So here's an example, right? So this is on really Rod from page 148 of your text, but I blew it up here so we could see it a little better. Here you have an income every week or whatever, $12. And the price of apples, okay, is $1.50 per pound, and the price of oranges is $1. We'll say B for oranges. I don't know why, but we'll just have $1. So there's lots of different combinations here of apples and oranges. Hey, you could just buy 12 oranges, 12 pounds of oranges and no apples. That doesn't sound very fulfilling to me. Or you could buy, 8 pounds of apples and no pounds of oranges, because 8 times 1.5 is 12. And you could spend all your money just buying apples. In fact, we can picture those two consumption bundles as endpoints of this budget line here on the right. Now, we introduced the budget line way back there. I'm kind of revisiting this today for a reason. But we talked about this before, okay? And we used this to derive a demand curve. In fact, we talked about this last time. It led to a picture in your book. But as you hold one price constant, say the price of A constant, this intercept will not move as we vary the price of B. This is the B axis here. So if you increase the price of B, this line, I brought my colored paper in here today. As you increase the price of B, this line's going to swing in like this. If you don't do anything to the price of A and you still got $12, this will come in. As you increase B, you have fewer consumption bundles to purchase. Hope that makes sense. As you decrease the price of B, maybe B becomes 50 cents or whatever, that budget line's going to swing out, and you can attain more consumption bundles that way. And so we use that. We vary the price of B under ceteris paribus conditions. That is, we don't change the income. We don't change the price of B. We just change, the price of A. We don't change the price of A. We just change the price of B. We were moving this line back and forth. Okay? So for each price, like for this one here, okay, if the price is $1, the quantity consumed is 12 pounds, okay? But if you double the price, the quantity consumed would be 6 pounds. That line's going to go like this, okay? And so there's 2 points on the demand curve. And so you could plot those in P versus Q space, P versus Q, and you're going to have a straight line that looks like this. And it's going to go through these 2 points right here, okay, at a price of $2. Okay, you'll consume 6 pounds. At a price of $1, you'll consume 12. I'm sorry. Okay, that's how you did it. Okay, that's how we did it. That's how you form a demand curve, basically. And that's how we're going to do it here in a little bit, but we're going to look at this in a little more detail. Okay, here's the deal. When I increase the price of B from $1 to $2, causing this thing to swing in like this, my consumption went from, my consumption went from 12 to 6. There were two reasons why that happened. There was the income effect and there's a substitution effect. Those two things we talked about. The income effect will be responsible for some of this, but most of it's the substitution effect. So say this amount is due to the substitution effect and this amount is due to the income effect. Okay? For normal goods, these two move together, as we just saw with that little arrow diagram. I said they move together, right? For normal goods, substitution effect, income effect move together. That is to say, I draw these two lines like this, and it's these two things working together that will cause this decrease in the quantity demanded of B. Now, if this were an inferior good, apples are not inferior goods, or neither are oranges, but suppose it is for a minute. Suppose good B is an inferior good. The substitution effect may go way over here. The income effect will be in the opposite direction. So you're adding signed effects here. There's one that's taking you too far and the other that brings you back, okay? Because they work in opposite directions, okay? That's one way of picturing this. Now, we have a way of kind of isolating these two effects, the substitution effect and the income effect, by using the budget line for a minute and then also talking about what are called indifference curves. So I want to go to this next concept. We're going to put two things together. So the first thing we're going to make use of here is what a budget line is. So hopefully by now you know what a budget line is. We were just looking at one. You should be able to draw a budget line. You should be able to find the two intercepts by taking the income and dividing it by the price of the good on that axis. Okay, you got 2 points, you can draw that. Okay, and so any point on this curve you can purchase if you want. Now, I don't want just apples and I don't want just oranges. All I want to mix in here. The question will be, okay, on your budget, what level of apples and what level of oranges gives you the most satisfaction? Okay, and we've been using this rational spending rule. Okay, and so it's some sort of bundle interior here. It might be this one. 6 pounds of oranges, 4 pounds of apples. Okay. And it all depends. If the price changes, that's going to change that optimum consumption. But at any rate, there's some point on the budget line that delivers the most satisfaction. And what I want us to get to today is I don't want us to just learn how to plug and chug numbers and so forth. I want to build a little understanding about how economists view this problem here. And half of the problem is by to getting a view of this problem and understanding of this problem is knowing what a budget line is. There's a budget line. So if you can sketch a budget line, you got it. Now, one thing about the budget line, before we go to the utility curves here in a minute, or indifference curves, is you should be able to find the slope of this thing too, okay? You think about what's the slope of that line. Notice it's the rise of the run is 8 over 12, right? So I'm going to just write this up here. M equals 8 over 12. It's really a negative number, but it's 8 over 12. Let's just say it's 8 over 12. Okay? Now notice, this is equal to the price of the good on the horizontal axis divided by the price of the good on the vertical axis. Now we see the slope rise over run is 8 over 12, right? I submit to you that that's always going to equal to the price ratio. The slope of a budget line is always equal to the price ratio. What do I mean by that? Well, the price of B is $1. So I'm just going to put a $1 here. The price of A is $1.50. So this is 1.50. Okay? So, if you divide 1 by 1.5, that's 2/3. Same thing as 8 over 12. So, if, say you have an exam question or something, say, what's the slope of the budget line? This is all I give you right here. This is all I have to give you. In fact, I don't have to give you all of that. All I have to do is give you these two things right here. I hope that'll clear up. There we go. I say, what's the slope of the budget line? Boom. This divided by that. It's the price ratio. That's an important thing we're going to make use of. So that's the first thing. Okay? File that away, stick that away, because we're going to marry that up with something else here as we turn our attention to these things called indifference curves. Okay, let's come back to this slide I was about to show you. Indifference curves, these are combinations of two products that yield the same amount of total utility. Combinations of two products that yield the same amount. So apples and oranges. Okay, I can buy a bunch of apples and a few oranges, or a bunch of oranges and a few apples. We're going to look here at combinations that deliver the same amount of utility. That is, the consumer would be indifferent as to which combination to purchase. So I want to show you what an indifference curve looks like. We'll come back and look at some more of this here. Again, I've given you some slides on this. You might believe you've looked at this. But this is a typical indifference curve. We got B on the horizontal axis. We got A on the vertical axis. So there you go. This is just like this. So, I mean, I can fill this out if I want, make a little Cartesian system. And I want to just think here about this. This is joining different consumption bundles, that is combinations of B and A that deliver the same satisfaction. Okay? They talk about J, K, L, and M. Here, if you look here, J, you're doing with less A, and you're adjusting by taking in your consumption more B. Because both these are normal goods and so forth. Well, just because more is better than less, really. More of A and B is better than less of it. I'd rather have more ramen noodles than less. Okay? It doesn't matter what my income is. If I don't have to give something else up to get ramen noodles, more is always better. I can always sell the extra or whatever. The idea here is more is always better than less. So if you think about it, I hope this makes sense for a second. It would always have to be the case that for consumption bundles over which you're indifferent, or you don't care whether I have this or this or this. I don't care. You shrug your shoulders. I say this week you're going to have a bunch of apples and few oranges. Next week you're going to have fewer apples but more oranges, so forth. Does it make sense that when you look at consumption bundles over which you're indifferent, that you would have to have this relationship, that if you increase one of the units, you would have to decrease the other, because more is always better than less. An indifference curve will always look like this, which is a graphical expression of what we just noted. More of one means less of the other to keep you at the same level of utility. Maybe the utility here is 24 utils. I don't know what it is. But if we could say how many utils here, you get a certain amount of satisfaction because you like apples. But gosh, you don't get very many oranges. So next week you'd say, well, I'll trade in some apples to get some more oranges. You could do that. There's a rate at which you could do that and have the same satisfaction. Now notice here, you give up a lot of apples to get a few more oranges. If you are accustomed to not getting many oranges, these are oranges, in your diet, guess what? That first few oranges, you're willing to give up a lot of apples for. Okay? First unit of of oranges. Now maybe you've been consuming 2 every week. Now you go from 2 to 4 pounds. You'll give up a bunch of apples for this next increment of oranges. Okay? But notice when you go from 4 to 6 in the subsequent week, you'll give up fewer apples to get a bump, the same bump in oranges. Okay? So what are we observing here, class? What do you think we're observing for good B here? You're observing diminishing marginal utility of oranges. The second couple pounds of oranges, you are willing to pay a bunch of apples for. The second one, not as many. So there's something here I hope you grab onto. Again, diminishing marginal utility will make an indifference curve convex. Convex like this. Okay, it's not only downward sloping, because more is better than less, but it's convex. At some point, initially to get a few more oranges, I'll give up a bunch of apples. But when I get up here where I'm getting a bunch of oranges each week, then I'm not going to give up very many apples to get another bump in oranges. Okay? And I can turn this around. Same thing is true for oranges. Okay? It's diminishing marginal utility. Oh, DMU. Okay? Diminishing marginal utility means that this curve is convex. That's called a utility curve. Okay? The utility curve joins consumption bundles that deliver the same satisfaction. Guess what, though? That's not the only utility curve. There's one here, there's one here, there's one here, there's one here. There's several utility curves, okay? As you go out, say, from this bundle, and you compare it to this one on another utility curve, you get more satisfaction on this one than on this one. And this one here, I could call it K prime, perhaps, because this is K, is equivalent in utility to L prime, which is equivalent in utility to J prime. Say if I draw the utility curve that delivers twice as much satisfaction as this one here does, I'm going to get a curve out here somewhere. Why? These arrows here will always go to the north and east, because when I go from here to here, I'm increasing both goods. More is better than less. So if you give me more apples and more oranges, I've been doing this every week, consuming 6 pounds of oranges and 4 pounds of apples, say. Every week I've been doing that. If you give me more oranges and more apples, I'm going to move this way, okay? And always go northeast, and I'll have more utility because more is better than less. So this might be for utility of 48 utils. Just say 48 utils. So you have this mapping here, okay? This is true for every consumer. This is just a math model. We're trying to describe how the world works here. This is kind of like a topographical map. Have you ever looked at a topographical map? You know, so you see those contour lines. Okay, so you might have a map of Oklahoma or something. Here's Oklahoma. And, you know, here's Black Mesa out here. And then you got these contour lines. What do those contour lines represent? They'll have a little number on there. Maybe this is 620. Elevation, exactly right. So this is 600 maybe, and it'll do something like that. And so elevation. Okay, that's what this is here. These are contour lines. I want you to think about this a second. These are contour lines corresponding to different elevations. Okay, so what do I mean by elevation? Okay, I'm going to reach here just a little bit, and I know this isn't, don't want to make this too mathematical, but the idea is in a multivariate sense, if we were looking at multivariable mathematics, what we do is above this plane that maps out quantities of x and y, we'll have a third axis here coming like at you. And on this third axis, there's elevation. And the elevation itself represents utility. Okay, utility. So it'd be like a hill. Can you imagine a hill over this, going up like this? Okay, if you slice that hill at different elevations, and you look at the shadow of those slices in the floor here, you're going to get these contour planes, contour lines. Okay, so these are contour lines. That's the point here. These are contour lines here corresponding to different utility levels that if I could plot this on a computer and rotate it around, it's kind of neat in calculus class or something to do that. And you say, well, that's a hill there. Okay, that's what that is. Okay, so we have on this third axis, which I can't draw on a two-dimensional sheet of paper, but on this axis is coming at you here, you have the measure of utility. It's an elevation, as you say. Okay, so kind of some concepts here, if you will. These are what indifference curves are. Okay, so more is better than less for both goods, so you always step up in utility going this way. But then these have to be convex because of the law of diminishing marginal utility. That means these are convex. All right, so as I mentioned here, utility curves are combinations of the two products that yield the same amount of total utility. They're downward sloping, they're convex to the origin, and they reflect this thing. Your book will define this term here for you. On page, I forget, Do you know, did you see? 149, thank you, Glenn. Page 149, okay? If you look on page 149, they will define marginal rate of substitution. This is the rate at which a consumer is willing to substitute one good for another and remain equally satisfied. Remain equally satisfied. So in other words, you have the same total utility. At what rate would you give up apples to get additional oranges to have the same utility? Okay? So it's a rate of substitution of one of the goods for the other. This is the marginal rate of substitution. And they'll tell you the rate at which you're willing to substitute one of these goods for the other is the slope of the utility curve. So if I were consuming 4 pounds of oranges, I don't know why it's sticking there, 4 pounds of oranges and 6 pounds of apples, I would substitute apples to get more oranges. At what rate? Well, the rate is called the marginal rate of substitution. Okay, looks like, hope that. And the marginal rate of substitution turns out to be the slope of this line that just brushes that indifference curve. Okay, it's called a tangent line. You notice that tangent line is going to rotate. Initially up here, I will give up a bunch of apples to get some more oranges. Down here, not so much. And over here, certainly not so much. The rate at which I will give up A to get B is the slope of this line right here. Okay? It's the marginal rate of substitution. All right, that is called the marginal rate of substitution. And the marginal rate of substitution is equal to, okay, first off, what we're saying here is the marginal rate of substitution is a rate. Is the rate at which we would give up A to get B, say. Okay? The rate at which we, now what is that, okay? It turns out that the marginal rate of substitution is equal to the marginal utility of B over the marginal utility of A. Now here's where we get three-dimensional again, and I'm just going to mention it here. If you don't follow this, that's fine. That's okay. I don't really, but it turns out if you look at this indifference curve, these indifference curves as being what's the term? What's the contour lines, right? If you look at them as being contour lines, just a second, you'll see that the slope of this line here can be found by comparing the slope of the hill going in two different directions. And I would just say this, that if this doesn't make sense, that's okay. I just say note that the marginal utility of A times the change in A is the marginal utility of B times the change in B between 2 points on the same indifference curve. So between K and L, these things here give you the slope of the hill in A and B direction. So here's B and here's A again. Picture this hill here. You're going to go uphill or downhill if you go this way, okay? So here you're probably going to go downhill, right? This is on a contour and this is on. So you're going to go downhill and then you're going to go uphill to get back to the same level. This is called delta A, this is delta B, and these marginal utilities are the slope of that hill in each direction. And that's all I need to say. I don't mean to make this complicated or anything like that. But if you take this thing right here, if you've had a little bit of math, perhaps that looks familiar to you. This is true between any 2 points on the same contour line. Then you can solve for delta A over delta B, the rate at which we would exchange B for A or A for B. Let's see here. I want to say, I said delta A over delta B. Let's put A on top. Delta. Here we go. So I can solve for delta A over delta B, divide through by delta B, and divide through by the marginal utility of A. So delta A over delta B, which is the slope of the line joining these 2 points here, delta A, delta B, delta A over delta B is equal to the marginal utility of B over the marginal utility of A. All right, okay, so all that's to say is I have 2 formulas for the slope. I have, first off, 1 formula for the slope of an indifference curve. The slope of an indifference curve, change in y over the change in x, but I got A and B instead of y and x, is the ratio of the marginal utilities. All right, so now I'm going to draw this picture, okay? This is the second thing to file away. The slope of an indifference curve is the ratio of the marginal utilities. The slope of a budget line is what? Remember that? Is the ratio of the prices. Didn't we get that just a moment ago when I wrote this thing right here? The slope of a budget line is the ratio of the prices. The slope of a utility curve is the ratio of the marginal utilities. Now they have a picture here in your book. Just put this up here a second. And I want you to think about this picture. And I know I'm kind of going through this, but this is just some concepts to think about. This point right here is the best you can do on this budget line. I'll consume X, that is to say 6 pounds of B, oranges, 4 pounds of apples. Do you see that if I can afford other consumption bundles on the same budget, but those would put me on a lower indifference curve or utility curve. We use the same term your book uses, utility curve, but usually here indifference curve. If I consume over here, I'm on a lower curve. I2 delivers less satisfaction than does I3. The goal of a consumer is this. Given your budget, so you got a budget line, select the consumption bundle, that is the point on this budget line that touches the indifference curve most to the north and east, that allows you to purchase the most, or the combination of A and B that delivers the most utility. This is where you want to be. On this budget line, which is created by increasing the price of B, on this budget line, that's the best you can do. That is to say, you have this tangency condition where these 2 things we've noted is true. Here's where a consumer wants to be. A consumer, given their budget, here's their budget line, wants to be right here. Right here. They don't want to be over here that's on a lower indifference curve. And of course they can't be out here either. That's unattainable. They want to be right here. Well, what's true right there? Okay, the slope of the indifference curve 1, is equal to the slope of the budget line. This point right here would say that the slope of the budget line equals the slope of the indifference curve. There's a tangency condition here. The slope of the budget line is the ratio of the prices. The slope of an indifference curve is the ratio of the marginal utilities. This is the slope of the budget line. This is the slope of the indifference curve. Budget line, indifference curve. All right, so what's that mean? Well, if this is true, the slope here is equal to the slope of that curve so that they just brush each other. I don't want this one, and I can't get this one, can't get that far out. That would mean this is true. Okay, if that's true, then I can cross multiply and get the following. Marginal utility of B over the price of B is equal to the marginal utility of A over the price of A. Does this look familiar? This is the rational spending rule, or the utility maximizing rule. Your book calls it the utility maximizing rule, but a lot of times you hear rational spending rule. conceptually, this is where this comes from. You know, we didn't put any calculus here, anything that's marginal utilities, or partial derivatives, and so forth. If you take a calculus 3 class, you'll learn how to calculate these from a utility curve. Okay. If you want to take more economics, if you want to take intermediate economics, you'll learn how to calculate these marginal utilities. But they give you the ratio of these marginal utilities always gives you the slope of an indifference curve. Okay. This is the marginal rate of substitution, the rate at which you would substitute A to get a unit of B. Okay? How many A's would you give up to get a unit of B? It's the marginal rate of substitution, it's the ratio of the marginal utilities. Whether you kind of followed me when I talked about the contour lines and a hill and so forth, you know, might think about that. Okay? So, but I think this might be kind of intuitive to us. You want to get out as far out to the indifference curve as far to the north and east as possible so that you're maximizing both of the two goods. When you do that, you will satisfy this rule right here because the two slopes are equal. Okay, so that's conceptually where we get, that's the model, okay, that's implicit in what we're talking about here. Okay, and we have determined a demand curve by increasing the price of one of these goods, as we noted a while ago. If you increase the price of B, then you bring this thing in, okay? And you get a different value for the quantity of B that we consume. All right. Here's two equilibrium positions. Your book gives you this picture. I forget what page this is on. Maybe Glenn can help me with this too. I just photocopied this. Here's a big budget. Okay, same budget, but you increase the price of B. Okay, notice what happened. When you increase the price of B, here's B. Notice when you increase the price of B, you rotate this thing, as we saw before. You rotate this thing this way. So you don't change the price of A, don't change your income. This is ceteris paribus. Just increase the price of B. The quantity of B that you'll consume and demand will decrease. It'll shrink. That's how we get these 2 points on the demand curve. Okay, what's the demand curve look like? It's got price of B going this way, and it's got the quantity of B going this way. And so what we've seen, we've got 2 points here, right? When the price of B is 1.50 the quantity demanded is 3. When the price is $1, the quantity demanded is 6. So as price goes down, quantity demanded goes up. How do we get this demand curve? The relationship between price and quantity is by looking at this indifference curve mapping. Notice here, this has just got quantity and quantity on the axis. Doesn't have price anywhere. Okay? It's the price that determines the intercepts, the price and the budget itself. Okay? But if you don't tweak the budget, you don't tweak the price of the other goods, say good A, you can sketch out here the demand curve for B by doing exactly what we've done. And what we said here just a little bit ago is that the quantity demanded will decrease in the face of an increase in price. It'll decrease because of two things. Remember I sketched this? I said there's a substitution effect and there's an income effect. Okay? Can you see that? Now, okay. I know I'm being a little theory. It's conceptual day, okay? We're thinking in concepts today. Now, how does that work for, this is a normal good. These two go together. They point in the same direction. If I lowered the price of B, this line over here, budget line would slope outward, would move outward, and these two things right here would go to the right. Okay. Now this is for a normal good. I and S move in the same direction. All right, so here's the last chart I want to show you here. Okay, I've given you this, or we put this up. Let me use this one instead. I put this up a couple nights ago. I don't know if you had a chance to look at it or not. But here's an indifference curve, and here's another one. And this is like, instead of B and A, I got X and Y. It doesn't matter. Okay? I want us to think about this just a second. Okay. Here, we've got a price, P1 of the good on the x-axis. And we're going to change the initial price, P1, for this good here, to P2. And you'll see over here there's a P2X here. So we're going to change the price from P1 to P2 for good X. We're going to break that down into two parts. Okay, the first part will measure the substitution effect. So we're going to increase the price from 1 to 2 for good X. Can y'all read that? So what happens? Okay, this intercept here is going to move from here to here. Okay, it's going to move from here to here. If, first off, we first stipulate that utility cannot change. So utility is going to remain constant over this price change from P1 to P2 for good X. Okay, so we're going to increase the price of good X from 1 to 2. Of course, that means by the substitution effect, we're going to consume less of the good. But here's what we're going to do. We're going to hold utility constant. That is to say, we're going to remove the income effect. We're going to compensate. That's a key word here. We're going to compensate the demander for the decrease in real income. Remember, if the price of a good goes up, real income goes down. Ceteris paribus. So if the price of this good goes up, real income goes down. So we're going to give this consumer a little bit more money so that their real income is fixed. And that will keep them on the same utility curve. We're going to give them just enough money to keep them on the same indifference or utility curve. So they get the same satisfaction. So what happens is you move from this point to this point on that utility curve or indifference curve itself. There's no income effect, just a substitution effect that's determined by the movement of this point to this point. So we're consuming less of this good, and we're only measuring the substitution effect because we're compensating. Okay, we're compensating the demander for the decrease in real income. We're going to give them a couple more dollars a week or what have you. And this is a substitution effect. And then, after we do that, and then we're going to take that couple of dollars back away from them, and we're going to see the effect on consumption or demand due to the income effect. And what you see is you're back to here. See, in your book, when we traced out the demand curve, we just held this in one point. We, as we did a while ago, we just went from here to here. Remember I said, oh, you can break that apart. I'm sorry, we went from here to here, okay? I said you can break that apart into two effects, okay? There is a substitution effect and there's the income effect that results from that. We went from here, that budget line, to this budget line. But actually, if you want to find the income and substitution effect, you got to break that movement into two parts. You got to rotate it around on the same indifference curve, that is compensate the demander for the loss in real income. So you're just measuring the substitution effect. That's this thing right here. And then you take that money back away from them and assume that they had the same income as before. That's what M here represents, income. And then divide by that price of Y on this price here. That gives you get the same point here. We're going to pivot about this point just as we did in the book, the example they give in your book. But this time we take that money back away from the consumer to see what the income effect is. So it's kind of two parts here, okay? Two parts. You compensate the demander and then you take the money back and you break this apart in income and substitution effect. Okay, so for an inferior good, you can do the same thing, but because an inferior good has a little different mapping here, kind of a skewed kind of thing, the income effect is opposite of the substitution effect, okay? They're opposite. Here they're in the same direction. Here they're in opposite directions. So you wind up here because you overshoot it with the substitution effect, as we noted a while ago. So I know there's a lot of concepts there, right? Okay. Hopefully this makes sense. All right. I know it's theoretical. We'll do practical stuff next time. Hope y'all have